So the final big idea in our thermodynamics topic is Gibbs free energy change. So you've probably been hearing the hints that I've been dropping along the way that when we think about something being exothermic, we think of that as downhill. Reactions that are exothermic happen very readily. If you set fire to a pile of sticks, they'll just keep burning. We don't have to keep putting energy in, the reaction just keeps going. And processes that increase entropy are also downhill as far as the universe is concerned. Anything that involves an increase in entropy we consider to be spontaneous. So if delta H is negative and delta S is positive, then yay, way to go, the universe is going to be happy with that. Okay, so if we put those two factors together, combine them, delta H, we need to change the sign of delta S because positive is good for entropy, whereas negative is good for enthalpy. And we need to remember that entropy is affected by temperature. The more temperature we have, the more heat we have. Higher the temperature we have, the higher the entropy change value. Put those two together, combine them, and give them a handy symbol to remember them by is delta G. So delta G is the Gibbs free energy change, and you're expected to know and remember that equation there. Okay, so going back to the example we had in the last lesson, so we had iron oxide reacting with carbon to make iron metal and carbon dioxide, and we calculated delta S for that to be, what was delta S? Plus 558.1 joules per Kelvin per mole. We can calculate delta H in the same way using delta HF data, and if you want to see that calculated, it's in the topic booklet. But let's just take it as read for the moment. Delta H for that process is plus 467.9, and of course that's kilojoules per mole. So we can now take those values and combine them. Notice that the delta H value is highly endothermic. So although entropy is definitely on our side for this reaction, because we're turning 5 moles of solid into 7 moles of stuff, including 3 moles of gas, enthalpy is not going our way. We have a really positive enthalpy change. If we want that reaction to go, we're going to have to supply it with a huge amount of heat to make it spontaneous. But let's put a number on that. So if we take our equation for Gibbs free energy, delta G is delta H minus T delta S, and put those values in. So delta H is 467.9, and then delta H, did I say delta S? Anyway, delta H is 467.9, delta S is 558.1, but we have to divide that by 1,000 to take account of the fact that delta S is measured in joules per Kelvin per mole, not kilojoules. So that makes our units correct. And if we did this at 298 Kelvin, then what would that give us? Well, it would give us a delta G of plus 301.6. And delta G, like delta H, is measured in kilojoules per mole. Okay, so what does that mean? Well, the bottom line is that if delta G is negative, then yay, the reaction is feasible. That's what we're looking for. That's supposed to be a tick. If delta G is negative, the reaction's feasible. It will go. If it's positive, especially a large positive number, that means it is not feasible. not feasible. Okay, so you might ask the question, well, okay, it's not going to be feasible at 298 Kelvin, that's room temperature. I wouldn't expect to smelt iron at room temperature. We're going to heat it up a bit, of course we are. How high? How high do we have to go in order to heat it? Well, I want to know the point at which delta G goes from being positive to negative, so let's set it to 0. If delta G is 0, then that's the moment at which the tipping point occurs. So now 0 equals delta H minus T delta S. I want to make T the subject of this equation, so well, T, if I move that over there and then divide it by delta S, T is delta H over delta S. Okay, now we just use those numbers again, 467.9 and divided by 558.1 divided by 1,000. Remember, we have to factor that in, 558.1 there. Work that out, and that comes out at a tasty 838.4 Kelvin. What's that in centigrade? It's quite hot, a few hundred degrees centigrade. But that tells us that if we get this reaction up to a few hundred degrees centigrade, 838.4 Kelvin, we will get a spontaneous reaction. In other words, at a high enough temperature, the entropy factor will overcome the positive delta H factor. If we can get it hot enough, this cancels out that and the reaction becomes feasible. Okay. We'll do a summary of that in a moment, but just to summarize our key thoughts about entropy there. So entropy is a measure of disorder of a system, and things that are more disordered will have more entropy. So therefore gases and liquids and aqueous solutions have more disorder, therefore greater entropy. And also more entities equals greater entropy. Have to be careful how you say that. Lastly, we can calculate Gibbs free energy using the equation delta G equals delta H minus T delta S. Don't forget to convert delta S by dividing by 1,000 so that you convert from joules to kilojoules to make everything hunky-dory. And if we rearrange by setting delta G equal to 0, it'll tell us the temperature at which the reaction is feasible. So an interesting little thing to do is have a think about the 4 possible states that reactions can get themselves into. We can have an endothermic reaction, or we can have an exothermic reaction. We can have an increase in entropy, and we can have a decrease in entropy. Remember, endothermic is bad as far as the universe is concerned. Negative entropy is bad as far as the universe is concerned. Negative enthalpy downhill, positive entropy downhill. So let's put the 2 downhill ones together. If I go with negative enthalpy and positive entropy, delta G is always going to be negative. Reactions feasible at any temperature. What kind of reactions are feasible at any temperature? Well, combustion is a good example. If I burn something, it's always exothermic, and I'm always usually turning liquid or solid fuel into gaseous carbon dioxide or whatever it is that we're making. So if I'm burning fuels, that should be feasible at any temperature, although it is quite hard to burn petrol if it's solid. Let's go to the opposite end of the spectrum. So if we've got positive enthalpy and negative entropy, delta G is always positive. So that means that we never have a feasible reaction. Okay, if you want to make diamonds out of carbon dioxide, good luck. You're turning a gas into a solid in a massively endothermic reaction. You're probably not going to get very far. Okay, it's the other two ones that are interesting then. So if I have an increase in enthalpy and an increase in entropy, that's the situation we had over here. Delta G is negative, or the reaction's feasible at high temperatures. Okay, so we just saw an example of that. If I keep heating it up enough, eventually I'll get to a point where I can make the reaction happen. Dissolving sodium chloride, we mentioned that the other day. It's got a positive enthalpy but a negative entropy. As long as there's a high enough temperature, I can dissolve my sodium chloride. Cool it down a bit and sodium chloride won't dissolve. And then the opposite over here must be that delta H is negative, or the reaction's only feasible at low temperatures. Now that at first sight sounds impossible. How can you have a reaction that only works if you make it colder? Well, a good example is freezing water. If you want to freeze water, the simplest way to make sure that reaction happens is to drop the temperature. Freezing water is exothermic. Heat's given out as the particles join together, but it's a massive decrease in entropy because we're going from disordered liquid water to very ordered solid ice.